Let me tell you a story. It's a story about a man who changed physics twice, only to spend the last decades of his life wrestling with a theory he himself helped create. It's a story about how the universe turned out to be stranger than even Einstein was willing to accept. And it's a story about a seemingly innocent idea, the belief that the world always has fixed properties beneath the surface, like a particle always having a precise position before you measure it, or a coin always being heads or tails even before you check. That belief ended up colliding with the deepest experiments we have ever done. So settle in. This is a tale of quantum mechanics, hidden variables, and the moment when nature said, "Einstein, I love you, but you're wrong." Einstein grew up in a world where physics meant clarity. A particle had a position, a particle had a velocity. The moon was there even when no one looked at it. Reality was crisp, definite, and objective. So when quantum mechanics arrived with its talk of wave functions and probabilities, Einstein was not a big fan. Before we digest Einstein's ideas, let me pause and explain what wave function means. In quantum mechanics, every particle, an electron, a photon, even an atom, is described not by single numbers like a position or a velocity, but by a kind of mathematical cloud. This cloud, the wave function, does not tell us where the particle is. Instead, it tells us the different places or states the particle could be and how likely each one is. It's a map of possibilities rather than a snapshot of facts. When we talk about a particle being in a superposition, we mean that its wave function spreads across several possibilities at once, the way a musical chord contains several notes at the same time. Einstein famously said, "God does not play dice." But what he meant was that the universe must be deterministic. What he meant was that physics should describe what is, not merely what could be, and so Einstein favored what we now call the ensemble interpretation. In this view, the wave function is just a statistical tool like a weather forecast. When we say there is a 30% chance of rain, we don't imagine the sky is in a superposition of raining and not raining. We just mean we don't know enough. Einstein thought quantum mechanics was like that. The wave function describes our ignorance, not the world. It's a beautifully intuitive idea. It feels natural. It feels classical. It feels like the universe we grew up believing in. But then came the trouble. In 1935, Einstein, Podolsky, and Rosen EPR published a paper that was meant to expose a flaw in quantum mechanics. They described a pair of particles that fly far, far apart. For a given property, like spin measured along some direction, quantum mechanics assigns a wave function for both particles together. But what happens if someone actually measures that spin on one of the particles? According to the quantum theory, the wave function suddenly collapses, and the possibilities shrink to a single definite result. Not just for the particle you measured, but for its distant partner as well. It's as if measuring one instantly forces the other to reveal a matching answer, no matter how far apart they are. Einstein hated this. He called it spooky action at a distance. His argument was simple. Quantum mechanics must be incomplete. There must be hidden variables, real definite properties. Einstein was trying to overthrow quantum mechanics. He was trying to complete it. He wanted a deeper layer of reality beneath the probabilities. And for decades, many physicists agreed with him. Then, in 1964, John Bell entered the scene. Bell was a quiet, thoughtful physicist who asked a deceptively simple question: if Einstein's hidden variables exist, what would they predict? He wasn't trying to prove Einstein wrong. He was trying to formalize Einstein's intuition. But what he found was astonishing. Bell showed that any theory with the features Einstein wanted must satisfy a mathematical constraint now called Bell's inequality. Quantum mechanics predicts violations of this inequality. Einstein's theory predicts this inequality always holds. So Bell said, let's test it. And when the experiments were finally done, first by aspect, then with loophole-free tests in the 2010s, the results were clear. Nature violates Bell's inequality. The universe does not behave like Einstein's hidden variable picture. Bell's theorem forces us to give up at least one of three cherished ideas. 1. Realism. The world has definite properties before we measure them. 2. Locality. Distant events cannot influence each other faster than light. 3. Statistical independence. The experimenter's choices are not secretly correlated with the system being measured. Einstein wanted a dream theory to keep all three, but Bell's experiments show correlations between the particles that are too strong for this kind of theory to explain. So Einstein's dream theory must be modified. And here is where the story becomes almost tragic, because each modification betrays something Einstein held sacred. Option A, add non-local hidden variables. One way to rescue Einstein's dream is to say, fine, let's keep the idea that particles have definite properties, but maybe they also carry some extra instructions, the hidden variables, that tell them exactly how to behave. That can explain Bell's experiments. But here is the twist. To make those hidden variables reproduce the experiments, they have to communicate instantly across space. This is the essence of Bohmian mechanics. In Bohm's picture, when you measure one particle, the other particle, no matter how far away, updates its behavior immediately, as if the universe has a private, faster-than-light messaging system running behind the scenes. And this is not just a metaphor. In Bohm's theory, the hidden variables evolve according to a pilot wave that stretches across space and updates everywhere at once. It's beautifully deterministic, mathematically elegant, and philosophically bold. But it's also non-local in the most literal sense. Einstein would have hated it. Option B, superdeterminism. Another escape route is even stranger. It says, what if the universe is arranged in such a way that your choices were never really independent in the first place? This is superdeterminism. In this picture, when you decide which direction to measure a particle's spin, whether you twist the knob left or right, that choice is not truly free or random. Instead, it's correlated with the hidden variables inside the particles you are measuring. Not because anyone is cheating, but because everything, your brain, your apparatus, the particles, shares a common history stretching back to the Big Bang. It's as if the universe wrote a script at the beginning of time, and every experiment you perform is just acting out a scene. You think you are choosing the measurement setting freely, but the script already coordinated your choice with the particle's hidden state, so that the results always match quantum predictions. This idea preserves Einstein's beloved locality, no spooky action, no faster-than-light influence. And it preserves realism. Particles have definite properties all along, but the cost is steep. It means giving up the scientific assumption that experimenters can choose settings independently of the systems they study. It means the universe is, in a sense, rigged from the start. Everything is pre-designed. There is no such thing as free will. Einstein would not have liked this either. Option C, give up predetermined outcomes. The third option is subtler but just as radical. It says, maybe particles do not carry a full set of answers. Maybe they only carry the answer to the specific question you ask. This is the world of contextual hidden variables. In this view, the outcome of a measurement does not just depend on the particle's hidden state, it also depends on the context, the exact way you choose to measure it. It's like interviewing someone who only prepared answers for certain questions. Ask one of those, and you get a crisp, definite response. Ask a different one, and the answer becomes indecisive, indeterminate. Contextuality preserves realism in a limited sense. There are hidden variables, but it gives up Einstein's dream that those variables represent a fully objective observer, independent reality. Einstein would have found this deeply unsettling. He wanted the moon to be there whether or not you look at it. Contextuality says, well, the moon is there, but some of its properties only crystallize when you ask the right question. So, Einstein's dream theory can survive only by abandoning the very principles Einstein wanted to protect. That's the irony. That's the heartbreak. That's the story. That is where the story becomes philosophical. If the wave function is real, then reality is fundamentally probabilistic and holistic. If the wave function is not real, then the universe must be non-local or conspiratorial. Every option is strange and forces us to rethink what reality means. Einstein wanted a universe where reality is always quietly definite, waiting for us to uncover it. A universe that made sense. Quantum mechanics gives us a universe that is consistent, but not intuitive. And maybe that's the point. Maybe the universe is under no obligation to match the expectations of a species that evolved to throw spears and avoid tigers. Our intuitions were shaped for survival on the savannah, not for understanding entanglement, non-locality, or the deep architecture of reality. So when the quantum world refuses to behave in ways that feel natural to us, perhaps that's not a flaw in the universe, but a limit of the instincts we brought to the conversation.